So let me start with the warning. This is work in progress. Meaning things might be wrong, not perfectly checked. All the usual disclaimers. It might all mean nothing. And the slogan of the talk is: we're not going to look at our algebras, we're going to look at Boolean algebras instead. So slogan. Yeah. Boolean. And we're not going to look at all Boolean algebras, we're going to look at countably presented Boolean algebras. Instead of finitely presented algebras. So what does that mean? We merely have a countable set of generators and relations, such that the Boolean algebra is quotient over the free algebra of generators by these relations. Okay, and as Sally pointed out yesterday, we don't have a ring R such that we can define the spectrum as morphisms into R. But we do have a generic object or initial object of this category, where R was the initial object defined from R algebras. The initial object here is 2, so 2 takes the rule of R. Yes, so 2 meaning 1 plus 1 bool, the thing with the 0 in it and a 1 in it, which are different. And we define now for B a Boolean algebra for finite countably presented Boolean algebra. But notice the bool. Spectrum will be, or this is morphisms, it's Boolean morphisms. P to 2. And I will later give another justification of the word spectrum here and I introduce first action. But I want to start with an example of such a countably presented Boolean algebra. So example, we can take the free Boolean algebra in countably generators. And we don't take any quotients, and we call this Boolean algebra C. And now, what is a morphism from C to 2? A Boolean morphism from C into 2. So spectrum of C. We can assign any generator the value 0 or 1, and there are no restrictions on this. And that's it. So that is a counter space to the power n. Counter space has been studied a lot, also outside of synthetic algebraic geometry. The police a lot older than this. And it's used for results like uniform continuity. We can define intervals with it, so it's a very interesting object. And there are some principles called limited principles of omniscience, which talk about counter space and about restrictions of counter space. And one of those I would like to mention is the big lesser principle of omniscience. And they say that for all algebra in counter space, we have here they're always 0. We don't have they're always 0. So this is some measure of how much can we tell of these infinite sequences of binary, these infinite binary sequences. And I claim that in the axiom system I'm going to present to you, this one holds. And for that I will introduce the first axiom of this system, because that's the I should have maybe stated that the goal of this talk is to state some axioms for synthetic algebraic geometry in this context of countably presented Boolean algebras. Just for those who just walked in. So axiom number 1. This is called stone duality. We say for all Boolean algebras, how to be presented, and the evaluation map from V into 3 to the power of 3 is an equivalence. For those of you who know classical stone duality, this axiom is well justified, and its name is well properly defined as stone duality. Classically, these things are the spectrum of V are the ultrafilters from V, which form the stone space, named after the same guy, of course. And that's also one justification you could give for 2 as taking our goal. And I claim this implies that this doesn't hold. Did I want to state something else about this? Yeah, maybe some minor results of this. One is we can define is stone. Not like.
I have one question. So is it crucial that's countably presented for stone duality?
Well, this is an action. You can state it for whatever you want. Classically, it's true for Boolean algebras in general.
Yes. So the question is now if we could. So would we have models if we at least for axiom 1 if we allowed Boolean algebras of any number of?
Yes, I think so.
Yes.
But some tricks that we want to pull involving finiteness. And especially in the end of the talk, I will give a sort of the pro-finite definition. There you like finiteness and countable things. Yes. Okay. So, but we can define a property of a type being stone, saying it constructed with a Boolean algebra, and it proves that it is the spectrum of this Boolean algebra. And I claim this stone is a proposition. It follows from this because if we have this, then B is uniquely determined, and you can do some math to show that this path is also unique. And furthermore, this means that SP, the spectrum, is an embedding from Boole into any universe of types. So for any universe we have that SP is an embedding. Okay, so I claim negation of W of L. Let's see that. Go up more space here. Expected to. So what's going to be the ID? The ID. Okay. I'm going to call this A of alpha. So this property for OK alpha K is null, and then is 0, and then this is going to be negation of A, right? I claim that both of these are propositions, and therefore we can take the disjunction and change it into a sum. Because if both of these are propositions, then this is the negation of this. This is a proposition as well. And so what does this give me? WLBO gives me a function from 2 to the power n into 2. Namely, I can for every alpha determine whether alpha is true or alpha is false. And this will give me an element of the spectrum, and we're going to work with that. So assuming f to be obvious. Let's have the map from front space to 2, given by indicating whether A holds. Okay. So now we're going to use this action, and that says f must be of an evaluation with an argument. So that would yes, phi of alpha should be the same as evaluating alpha of E for E for some. And in the C, which was again the set of the span of these counter-Riemann generators. Okay. Now we're gonna use something. So E is in the span of counter-Riemann generators. In particular, E is a finite combination of these generators, and that means that we only check finitely many entries of alpha as a sequence. So this means E is finite. So alpha of E by an initial segment of alpha. So what do I mean by this? I mean that alpha is this infinite binary sequence. I can evaluate alpha at E. This only checks finitely many entries of this alpha, and I can sort of take the largest entry and put all everything there. That means this property is uniquely defined by this initial segment. But now I'm going to claim A cannot be determined by an initial segment only. Determinable, is that a word? Determinable. And why is that? It's because the property is that alpha k is 0. And I can, on this initial segment, always be 0, and then afterwards be 1, and this evaluation alpha E should not be able to make a difference between these two expressions. And that's a conclusion, right? Yes. So the conclusion from this is that we have a model where we have a counter space where the negation of W obvious, and this is cool. For people who are interested in principles of conditions and for the purpose of this talk, UI. Okay, that's good. Time. Okay, yes. Now let me state and prove another consequence of axiom, and namely that we have some sort of compactness in the following sense for stone spaces, stone types. Suppose X stone, and we more an X including natural numbers. Then now. Someone has a question about it? No. For stone space, any map out of stone space is bounded to natural numbers. Why is this? And it's a decidable set. constructively, yes. So for any n, we can define sort of the partition of X, which is a decidable partition on X. Okay, good. And we have a decidable partition. So wait, let's say, I mean, of course, indexed over n. Otherwise, it's not a partition, right? Because everything in X gets sent to some n, so everything is in the invert image of some n. And these are decidable sets because n is decidable. And these are disjoint because of the function, right? So I have a decidable partition, and I'm doing the similar trick to what I did over there, is I can make a map into 2 from this. I say I have a decidable subset, so I can make a map of X into 2 of this. So let E n from X into 2 indicate decidable subset. Of course, this again is going to correspond with some elements of some Boolean algebras by axiom 1. So we get this one with a tilde and this one with a so b is 2 to the power x. So note that here we have, I did some trickery here. Here I did a map into 2, and here it is something of 2 to the power x. We can define this if we have a map into 2, but of course it's not the same thing. A Boolean morphism into 2 is not the same thing as internally a map into 2, or 2 to the power x in this case. But we get these elements, and these elements have some nice property, namely that if I do if I take this quotient, I'm going to get something trivial, right? Because everything is going to be equal to some fn, so I cannot set everything to 0, every en to 0. So this is 0, and this means that B is spanned by these elements. So B is B is spanned by the elements, particular 1 is spanned by this element, so 1 is a ring combination. I'm talking about Boolean algebras, but Boolean algebras are fixed under some isomorphism, which I will not sketch out, but you will use. So this is a finite combination of EI times EI. And now I'm going to do some trickery. All these EI are disjoint. They can both be true at the same time when m is not equal to m. Otherwise, you know, f of 2 things is going to be equal to the same thing. It's going to be equal to two different things. This cannot happen. So we have this, and this means we can replace the sum by a union, because the sum is a disjoint union of elements. And the product is of taking wedge, and we can remove this wedge because we are removing a wedge only makes your things bigger, right? So we now have a finite union over 1, and I can even cut off this union because unioning with bigger things is not going to make it bigger, but it is finite. But this means that everything in X must be sent to something below n. Right, so this finiteness of this Boolean algebra, no, that's not true, it's not finiteness of Boolean algebra. Finiteness of the expression I get in my Boolean algebra gives me this boundedness. So that is yes. So this means that any map into a stone space is bounded. One particular corollary is that n is not a zone space. So you can come up with some maps from n to n that are not bounded. But you can yes. You can do something similar to n, and that's going to be something we can have countable zone spaces, and that's going to be my next example. So another example of a Boolean algebra. This is this be infinity. The generators are still countable set. But now I do take a quotient, namely quotient that I quotient out two things. I said the intersection is always going to be zero, or the mean is always going to be zero if you are not equal. So how you visualize this happens to be finite cofinite subsets of natural numbers. What is that? These generators are then the singletons. So the mean between the intersection of two singletons is always going to be empty, and if I keep applying Boolean operations, I'm going to stay finite cofinite. Infinity. Subsets. Okay, good. So we have B infinity, and now what is the spectrum of B infinity? I denote this to be n infinity. And so what is a map from this into two? I can send generators to either 0 or 1, right, still. But if I send one generator to 1, I cannot also send this generator to 1. Because their intersection must be 0, their mean must be 0. So I think about it as sequences who hit 1 at most once. Also remove this 1 at all, I can send everything to 0. And so what is a sequence hitting 1 at most once? I hit 1 at, say, a sequence or at an index in n, or I don't hit 1 at all, and then I'm infinity. So, and this classically is also the 1 point of compactification of natural numbers. So that's the intuition I have for this object. And there is another principle of omniscience we can state about n infinity. And this one we will variable. This is the latter limited principle of omniscience. So for n infinity in the sequences image. And well, we cannot determine it's always going to be 0. It's not always going to be 0 for vector space. What we can determine here, or that will turn out if I state one more action, is you can determine whether it's going to be whether it's always going to be 0 on the odd numbers or on the even numbers. So we can make this distinction. So I did where I did this one so much, but so now I have stated the lesser limited principle of omniscience, and I want to point out that this can be shown if we have sort of a surjection from n infinity plus n infinity into n infinity. Hitting on the left side doing all the odd numbers and on the right side doing all the even numbers. if this is surjective, and to prove this is surjective, I'm going to state an axiom. It's not how proofs work usually. So it's to be proved. And that between spec corresponds to a map between the power levels, right? If and only if such a map is injected. So you can okay. We can say this call this action formal surjections are surjections because such things you call formal surjections. Another name for this action, which I want to state and take some explanation, is called completeness. And that is because of something Hugo said and you had a discussion about before we started, is that this axiom sort of should be equivalent to for stone spaces. Being non-empty means being merely inhabited, and yeah, the idea why this follows from this is if something is non-empty, 2 to the power of u is not going to be trivial, and therefore the spectrum of u is going to be merely inhabited. And why do I call this completeness? That's or why is this called completeness? That's because we have this intuition that the morphisms from B into 2, so the spectrum of B, is in some sense is an evaluation. It's like this is a truth table, right? So this is a model for your Boolean algebra, where your Boolean algebra is now a theory. And then this says if my theory is consistent, it merely has models. So this is why you would call such a result completeness, right? This is a logical thing that we do.
Sorry.
Yes.
So you said this follows context.
Yes.
And is it equivalent?
It should be, yes. Let me not prove that. Let me put that in the work in progress disclaimer that I'm not going to prove this. But yes, they are equivalent. Okay, so good that we have 2 axioms. Not doing very well time. Oh, maybe. Okay. So yes. So to show that this is projective, we need to show that the corresponding map, which I from B infinity to B infinity down to B infinity, must be injective. And what is this map? It's an pk. It's a odd number. Numbers is 0 to pk. And this is injective. And I claim this clearly so. So it's very nice. This concludes LVO follows from it. So this is injective. And by action 2, this map is therefore share injective, and therefore LVO is verified with these axioms. If you can find all of these axioms, you have a model where negation of W LVO holds and LVO holds. That is very nice. That I want to sort of now highlight that we use this axiom in a non-trivial way in the following sense. I claim this map this map F has no retraction. Yeah, I'm first want to prove this claim, and then I want to point out some results motivating action number 3. So why is that it has no retraction? That are the retraction of F. We can use this to say, so R of 0, 1, this is going to be 0 bigger than R 0,3. Okay, right?
What does it matter? I mean, it doesn't matter, but
R.
R.
Yeah,
okay.
sorry, my I tried to write in block letters and say cursor gets in the way when I actually do math. But yeah, it's an R. So this is going to be bigger than, what was this? P2K. Okay. And similarly, our 1.0 is going to be bigger than P2K. This one. Okay. So what is now the ID? And this is a technical detail I'm not going to work out, but I'm going to only give you the ID. That Pn not occur these are finite Boolean expressions. Again, they must be because they're elements of being right? Finite, we have countably many generators. Therefore, I can find a generator outside of this finite set, and I can even find a whole lot of them. And I claim that if Pn doesn't occur in R0,1 and Pn also doesn't, then you cannot distinguish Pn and Pn with these elements. And you can formalize this. This is something that I'm not going to do because it's too technical, but we have done it and it's you can do a conjunctive normal form argument, even prettier because of this and co-finite business. Yes, okay. So I say that so if R0,1 is bigger than Pn, so if I cannot distinguish between them, the calculation that this means this is going to be this should not go any different when I do it for Pm instead of Pn. I hope this makes sense, and you are convinced that you can prove this. Okay, so it follows from this that these are going to be bigger than both of them are going to be bigger than an infinite number of generators. So we can find so they must both be bigger than some generators, right? Namely, after we go over this limit, all of them. So not only is R0,1 be bigger than P1, Pn for some n, for the same n, R1,0 bigger than Pn. And why is this a contradiction? That is because their meet is now going to be bigger than Pn, but their meet should also should be a Boolean morphism, so it should be 0, 0. So we get 0 is bigger than some generator, and if we cannot have this, right? That's a problem. So F is no retraction, proof is claim. And I want to, so LPO, in this sense, we cannot just we didn't need to use this action because we cannot take a retraction and just transport this along this anti-equivalence. We get a section and this will prove some subjective properties. And so why is this relevant? This means that an infinity is not projected. Okay. Yes, and this leads me sort of as a motivator because we do like some sort of projectiveness results, or projectiveness geometry, and we're going to state something close to that as action 3. And that's going to be that the arbitrary types here stand by x, and the more and write them like this, maybe it's found some spaces. So we have this situation. Have a stone space one. We have some morphisms. Let me choose this with another color. So this is some projectiveness result. Like projectiveness will be that we have this morphism, and we don't have that, but we sort of have this projective cover by stone spaces. But this axiom I hope to have motivated by saying n infinity is not injective, but not projective, but we want some results resembling projectiveness. Okay. Let me see if I want to state something else. Yes, okay, so also, yes. I now want to switch gears a bit. I've stated the first 2 axioms, and I want to motivate the last axiom by doing something actually resembling the title of this talk on the side, pro-finiteness, so like condensed. There's a nice way to work with countably presented Boolean algebras. And that is the perspective taken in the exact namely that countably presented Boolean algebras can be seen as co-limits of finitely presented Boolean algebras. So you are. So what I mean by this, I mean that I have a sequence of finitely presented Boolean algebras, and the limit of this will be countably presented Boolean algebras. And conversely, if I have a countably presented Boolean algebras, I can write as the co-limit of such a sequence. The sequence is not only unique, of course, right? I mean, you can always put off the third part, and we can skip over as many entities as we want, and we still have the same co-limit. As many finite and many entities as we want. Or countably in a smart way, but so let me sketch for this. Well, just the rationale to start. Okay. So suppose I have a co-limit, then on finitely presented Boolean algebras, I claim given by co-limit generators. For the co-limits relations. Okay, that's one direction, and the other direction. So this is co-limit finite, countable co-limit over finite sets of course countable. So this is all countably presented. And the other direction is I have countably presented Boolean algebras. You just say Bn is going to be the generators. And so I have an enumeration, and I can do this with some full proposition. Merely, I say they're merely represented by the sequences. I see some confused letters, or just people going. First generators over relations.
I mean, there's nothing special about Boolean algebras here.
No,
But yeah.
Really, actually, everything I'm about to state, I think, is true for nothing special about Boolean algebras. Algebras is good. Rings is good enough. The general algebras have kernels. No, we want this. Something like this. Yes, okay, let me switch up the order a bit. Okay. This is a result where you finitely presentedness. Finitely presented Boolean algebra. I think it also works. It's compact. In the sense, because compact. A lot of things about compact, and they all need something different every time you see it. In the sense that a morphism, let's call it A0, morphism from A0 into the co-limit into such a co-limit is the same as the co-limit. You can also make a sequence of morphisms from A0 into Bn, and then the co-limit of such sequences correspond exactly to morphisms from A0 to the co-limit. And I actually want to say something stronger, namely, I always forget this, the specific morphism composing from Bn to B is going to be, yeah, so the morphism from A0, a morphism in the co-limit is given by something in the sequence, right? That's how co-limits work. So the morphism from A0 to Bn is going to be sent to A0 to Bn. This is the co-limit projection. So this is an equivalence. So the trick is you use finitely presented something that goes over here. If finitely presented also means finite. Finite in the co-limit means we can contain it, we can find it all somewhere already in the sequence. And that's where you stop it. That's good enough. That's my proof and baby sketch for this. Okay. So what is now the motivation for action number 4? If that's is that with A can be bool and F with Boolean also, of course. You can always use choose presentation. I mean a presentation, I mean a sequence converted to B. Yeah. And a sequence of morphisms U and L and Bn. So here A is also given by a sequence already, and the claim it doesn't matter which sequence you pick. So I'm not constructing AN as well. So instead, mu, this is mu0. So we can sort of write this so that all of these colimits are in isolated. Let me maybe say first what is about this. I claim you can prove it if you assume one direction and state the action is that the order. Where did I leave my? I want to keep this one there. Anyway, I think I can do the whole this one, and I'm going to use that result so not to have it on the board. With corollary of this thing I have proven. I can always look at the kernel of these things, and I can also look at the kernel of this thing. Right, so I can consider okay. I can do this, right? It's this representation. Because of this result, this is also going to be the colimit of all the kernels over here. Right? Because I just quoted out more things, and it means I add this quotient of relations, this becomes a bigger set. So this is going to be the colimit of all these things. And what is very nice about this is that we know we can characterize projections by one of these things being isomorphisms and injections respectively. And that means that we can also, if these are all isomorphisms, all of these can, well, we can represent D by this sequence, right? So that means that a surjection can be represented by a sequence of surjections, and an injection can be represented by a sequence of injections. And this is somewhat of an individual. So projections. Colimits. Question. And the same goes for injections. Okay, so this would be nice. And let me so what do we do? We start with A0. This is a morphism into A. We go to B. We have a morphism from A0 to the colimit of a sequence. This means using that lemma, we have a finite point somewhere where we already have this morphism. So we can find some Dn such that this commutes. And we call this Dn0. Right, and so this becomes our D0. Then what we want to do is want to do the same thing for A1, and I'm going to sketch from here also due to time reasons. So we can do the same for A1, right? This is kind of an example. And I'm going to call this one B and one tilde. So I will talk over it, so for those of you who are taking notes, finally represented here into a colimit, therefore into a sequence. Therefore, we have a colimit of morphism from A0 to Bn, and something that appears in the colimit already appears at some finite place. That's how you get this in 0. That's how you get this in tilde. The problem, however, is that I have this also have this map. And I have the Bn0. and I have no idea if this commutes. I don't even know that BN0 comes before BN1, right? The way we set it up, we don't have this per se. But what we do have is that eventually these morphisms should be equal by this construction. So there should be a BN1 bigger than both of these, such that the morphism from here to here to here to here and from here to here to here to here do commute. And this is the this is actually the thing we pick. So we define not this morphism, we take this morphism for a sequence. And that's how we do it. But we are sort of iterating, choosing something bigger. So I'm using the axiom of choice for this argument to work. And yeah, let me write down the axiom of choice that we have in our math theory, or sort of that I'm going to add as an axiom. It's going to be dependent choice, so that we can actually do this. So that motivates the final axiom is want to get. And I always have to look this up because it's and maybe discuss how exactly we use this version of the axiom of choice in this argument, but it's more about we have some version of choice. That's the last section. So then, like, I also haven't remembered the details from the top of my head. That's my excuse. It's okay. Yeah. Yeah, this one. Oh yeah, I will have a look in place. Yeah, there's more mistakes in our draft, by the way. Then given the starting point, this new dependent function satisfying relation. Okay, so yeah, that's also, sorry for the rush in the end. Main takeaway is that the actions we propose when we change from R algebras to Boolean algebras are these four actions. And at some point there was some hope that these four actions are verified in light condensed set. This hope is not completely gone yet, but there was also some hope that we can replicate some results from these actions only. And there we are now a bit more careful. But yeah, that's the conclusion. So main idea is we have these four axioms, and you might be able to do stuff with them. And well, that's nicely within the hour. Thank you. And are there anything?
I'm curious about you talk about different Freek classical principles.
Yeah, the principles of conditions.
But do you know the status of the Markov's principle?
No. What is Markov's principle? Can you state it?
So in this language, you can say if you have a point of n infinity that's not the infinite point, which is the final.
So those. Well, infinity. Yeah, the negation of this means
can read it by saying like if a program doesn't work forever, then at some point.
And is this truncated or it is not truncated?
So you don't have to truncate.
Oh yeah, you're right. It's can only be one thing.
Or yeah, I mean, if you take a temporal sequence alpha, you can do it on the first block.
Or maybe we want to state it as like this.
No. That's the
So we have these two techniques, right? One we have the scoring technique, and the other technique we have is this corresponding element technique, if it does exist. So I do want to sort of, in some sense, I would prefer to look at the adjunction to this, right? Because then we have a D or an and, and this we can translate nicely. So how does this implication? So the question is, how does this implication sort of translate to the Boolean algebra underlying?
But the problem is like n is on the stone space. We kind of this is kind of saying that the complement of infinity and that infinity is m.
Yes.
But these are not stone spaces. So I don't know what you can something different.
Good question. That's yeah, I don't immediately have an answer for it. You should think about this. So what do we? Maybe, okay, are there any other questions regarding the talk? Maybe otherwise we will talk about this a little bit.
If I understand correctly, you said at some point we have less hope now that the axioms are modeled.
No, sorry, okay, so there was a specific trick that the Schulze uses that we are not allowed to use. And so the hope that we have less of is the hope that we can reproduce our Schulze's results from these axioms. Because he at some point used a trick that if you have this representation, you can choose all of these injective. Actually, his trick was to do this, so you have limits of things going the other way. You can choose all more surjective there. And there you use some, we can just not recognize if if an element eventually gives a finite field. Okay, maybe I should say a little bit more on this. So purely to this, we have we can state this in stone spaces. We can state every stone space is the limit of finite, right? Yes, finite stone spaces. Yes, finite. So we have finite sets, exactly. Yes. And then a trick that he uses is that you can choose all of these surjectives. And why can you do this? Is if you have an element here, you can sort of whether it shows up in X is let me rephrase this. For Cantor space, we have that X are the infinite branches of a binary tree. Similarly, here X is the infinite branches of the pre-images of the sort of the images you get here. So those branches go on forever underneath these things. And what is now the idea is if a finite branch of the tree that you get if you take pre-images here, this will not show up in X, and you just remove it from X0. You just remove every node that eventually is not hit anymore. But this requires us to sort of go infinitely deep down into the tree, and we cannot necessarily do this. And so Schultz has access to that, and we don't, and that might be a problem. Or we, at the moment, can't use the same trick. And I have less hope that we can reproduce Schultz's result because of this.
So maybe I will formulate this differently. So what it does is something external, and it's using LPO externally. But this cannot be done internally because internally we have not LPO. So the hope is still that these axioms captures everything that you can do internally. And there are some things that doesn't all instantly.
So confusingly, he proves what's internal reproducibility, it doesn't hold internally.
And so, again, a question about the countability. So, what breaks down and replace n, so the natural numbers, by some other infinite ordinal? So, I mean, the argument about the code limits. I mean, then the secret will just be a little bit longer. But then, of course, your dependent choice axiom.
So no, it's about this sequence is Schultz at least. So when you talk about Leibniz, you talk about not sequences, but you talk about diagrams over co-filtered filtered coordinates or co-filtered limits. I always forget which ones. And we represent those as a sequence in some sort of cofinality result. And the result that we use is that if the diagram is countable, you can make this in, well, okay, you can always linearize the sequence, but in this linearization, you might lose the property that all your coordinates are finite. And this might be a problem, I think. So this is a discussion I had yesterday. This is very catchy, like there might be one disclaimer here. So, yeah, I think that might be the problem.
Okay, you say the limit points.
Yeah, so yeah, I translated from these co-limits over filters, over kappa filters, let's say. If the kappa filters are countable, you can go to sequences.
Yeah.
You can always, yeah, because over n still in finite sets.
Mm-hmm.
You cannot do this linearization and remain in finite sets. If you do it for general volumes. I think.
Yeah. I mean, at the limit points of the larger ordinal number, you generally won't have anything.
So for those of you who don't know what this co-filter limit is, it's a little bit scary. It means that whenever I have a diagram, I have a co-code. So how do I linearize such a thing? Whenever I have a branch, I just say I take all of these branches and I take this into the next element, and this way you get sort of a sequence or something linear, calling it a linear diagram. But if this branching is big enough, this coding might not be finite, and that's the problem.
Yeah, I mean, if it's a problem.
Yeah.
I mean, the code limit still is given by.
Yeah, but then we also do things like this things, like this finite. Okay, so we still have this compactness for coordinates that we then add.
No,
I mean, you have it over different bit.
yeah,
So the coordinate is kappa filter.
yeah.
If A0 is kappa.
Yeah. I guess we can. Yeah.
Right.
Yes. Yeah.
So I mean, another problem is that if you want kappa things, I mean, how will you formulate axiom 1? Because internally you need to have a notion of kappa presented, but this kappa is not the same internally. For countable, it's the same in the model externally. So it's
Yeah.
clear how you will formulate axiom one kappa prediction.
Yeah, kappa should, I mean, there should be some kind of internal.
Yeah. Let me also state that because I haven't mentioned it when I was talking about this this SP being an embedding, but countably Boolean algebras are universe stable. And if you have a kappa over all universes, we can also do this, of course, for we also have some sort of stability. So, however, no matter the universe I'm working with, the countable Boolean algebras will always be the same, and this is nice.
Yeah, okay.
But I guess you can replace countable with kappa here.
Yeah, what the axiom form would become too strong,
Yes.
because then it's no longer dependent choice. I mean, we're going more and more towards the axiom of choice.
Yeah. But by choice.
Yeah.
And this is and this you can still do, of course.
Okay, thanks. Good.
So this last bit before, what kind of results are you looking for to, what kinds of results of Schultz do you want to prove? Because he does a lot of stuff with these condensed sets.
And so far, lectures 2 and 3.
So these cohomology, or is this analytic stacks lecture?
No, that's it.
Yeah, I haven't watched those.
Yes. And maybe something that so I didn't really go do an outlook, but yeah, that's some full stuff for the outlook. Yes, so we can talk about schemes and affine schemes, right? So, for example, the stone spaces are now the affine schemes, and the schemes should be things that have surjections from stone spaces into them. This is a direction generalization, and well, I say that these principles of omniscience, but we can also use Cantor space, for example, to study some non-standard analysis, or even standard analysis. It's already quite cool, right? So we can maybe. So the hope is that we get an interval object out of this Cantor space, for example. And I didn't follow the lecture of yesterday very well, so I'm sorry for this, but. So if we have intervals, can you maybe talk about curves even in this sense? These are
talk about
curves.
curves. Yeah, I mean, you can do real topology.
Like trying to define singular homology sets.
Yeah.
So this is for almost be. I mean,
And let me also mention Xu and Escardo wrote some things about things you can do in the isomorphism class of Cantor sets. The isomorph category of things isomorphic, the endomorphisms of Cantor sets to itself. You can do a lot of stuff in this. Very cool.
But and you know they're doing the side condensed it's not actually in the category but in the cover. We don't have the full concentration actually in the rest.
Yeah, excellent.
But it doesn't.
Yeah, that's also this extra covering condition that you have in light condensed sets. So certain sets are also covering. Yes.
Like the category of light for finite sets doesn't look exactly like this one-on-one category, but they have the same features. The difference is
And then the different sides, yes.
So, and to answer, so we hope to be able to prove that, stone space and Hn of x, z is 0, x is and then limit for x compact for z, Hn of z is the same, similar. With cohomology.
mean, like,
So this should someone, what is the condensed chronology of Schultz?
Yeah, yeah. So hopefully this follows the changes. Work with progress.
Okay, so thank you, thank you again. Have a break until 11.